Hello students, this is Professor Chalai, and in this video I'm just going to go over a very brief video going over some of the things that you might need to know for the gas emission spectra lab on Pivot Online. Alright, so we learned that in the Bohr model of the atom, we can think of electrons as going around sort of these orbits around the atom where he's assigned them specific n levels. N equals 1, 2, n equals 3. And so whenever an electron jumps from a higher n level to a lower n level, the energy that it loses is usually sort of emitted in terms of light. And we talked about how the energy of that light can be calculated using this equation. RH is the Rydberg constant, NF is the final energy level, and I is the initial energy level, and we square them. And RH here, let's use a different color, was equal to 2.1799 by 10 to the minus 18 joules because we're looking at energy. In our pre-lab, we're going to use this equation, or a very similar equation, to calculate the wavelengths of light emitted using the Bohr model. And they will write the equation slightly differently, so don't get confused. But they'll write it in terms of wavelength, and so they'll write the inverse of wavelength is equal to RH over the same idea. Then they'll have initial value squared minus 1 over final value squared. Now, where initial and final goes doesn't really matter too much because we're only looking at the wavelengths of light in this case, not necessarily whether energy was absorbed or emitted. But the other thing that you want to note is that in the lab, they use a Rydberg constant for hydrogen of 1.0974 times 10 to the 7, 1 over wavelength, right? These two numbers are very different, but they refer to the same constant. Because in one case, we were looking at change in the energy. In the second case, for the online lab, we're looking for the wavelength. Now, I just want to show you that these two are not the different. All that they use was this equation for the energy of a photon, E is equal to Planck's constant times the speed of light divided by the wavelength. And so to convert energy to wavelength, or 1 over wavelength like they did, you just divide both sides by h times c. So if you take this energy and then divide it by h times c, you should get the Rydberg constant in terms of inverse meters. Okay, or 1 over meters. So if I were to use this second equation, the wavelength then of light that's emitted is just 1 divided by the Rydberg constant that I use here times 1 over initial value squared, right? This should be squared, minus 1 over final value squared. And this will be in meters. However, the other thing that I want to point out is that since visible light is in the nanometer range, right, between 400 to about 700 nanometers, 400 nanometers to about 700 nanometers, it's more convenient to convert wavelengths from meters to nanometers. And so just to remind you, 1 nanometer is 10 to the minus 9 meters. So we need to use that conversion. So in our lab, we'll explore, in this virtual lab, we'll explore the different emission lines for a specific gas, and then we'll need to calculate the various wavelengths of energies that it emits from. The other thing that I wanted to point out was that the difference between absorption, hang on, let me zoom in a little bit there, absorption versus emission. I hope I spelled that correctly. So absorption just means that light was absorbed by the atom. Emission just means that light was emitted from the atom. So in absorption, you go from a low energy level to high energy level because the light that you observe converts to energy. That energy excites the electron from a low n value to a high n value. On the other hand, for emission, you go from a high energy level to low energy level, right? So you go from a high energy level to a low energy level, and the energy difference that you lose is emitted as a wavelength of light. So what do these actually look like? Well, if you're looking at an emission spectrum, you'll see the very specific lines of colors that are emitted. So let's say you'll see a few lines of colors. In the absorption spectrum, right, that's energy from light that is absorbed. It's completely the opposite. You would shine all the colors of light at an atom, and then the atom would absorb certain colors of light, and then everything else is what you'll see. So what you'll end up seeing, and it's difficult for me to draw this, when you look at absorbed light, you shine all the colors of light, and then what you end up seeing is some colors are missing. So I'll draw that as black. Some colors might be missing. Why are they missing? Because they disappeared because they were absorbed by the atom. So there we go. That's absorption spectroscopy. Absorption spectroscopy. Spectroscopy is just studying something using light, and emission spectroscopy would look something like this. Let me put some nice colors in there. You'll only see these colors. There we go. And this would be emission. I feel like emission has one M. Maybe. Spectroscopy. All right. So that's the difference between absorption and emission. It's just whether something was absorbed, in which case everything else remains that wasn't absorbed, or emission, in which case only specific colors were emitted from the molecule. All right, and the other thing I want to point out was don't get confused by the two different Rydberg equation with the two different Rydberg constant. In one case, it's for energy. In the second case, it's for wavelength. All right, that's just all I wanted to go over. This pivot lab should be very simple. If you have questions, though, please message your instructors and we will happily answer them. I'll see you in the next video. Bye.